All right, these are the first notes, and it's really the rest of Unit 2, but we're going to call it Unit 3. We're still going to be taking derivatives. We're not quite applying them yet, but it's on the horizon. We're going to take the derivatives of functions within functions, functions that we call implicitly defined, and then inverse functions. This is quite a bit more difficult than the other rules you've had so far. So I would suggest in this next unit here, you really focus on not doing this stuff just to complete the task, but to understand it. Because I would put today's rule, it's called the chain rule, and it's used for finding the derivatives of composite functions or functions within functions. And I would probably put it in our top 3 of most important skills we learn in here. So maybe top 5, but I think it hit the top 3. So this is a really important section. I'm going to Edpuzzle these notes, and then at the end I'm going to tell you where the rest of the points come from. So there'll be 7 points, test points, Edpuzzled, and then there's going to be 3 more that I'll explain to you how you should get at the end of this video. So really important one today. So first step, we've got these right here, functions. And these are just functions y equals f of x. They're just a function of x. And we have a rule for finding the derivative. We do the power rule. We bring the power out front, drop it down 1. All constants derivatives go to 0. For the derivative of sine x, that's just explicitly cosine x. For the derivative of basically any line, it's the power rule, but it's really just the slope of the line. And again, it's good to see that one. You don't need to draw this, but 3x plus 2 is going like this. And if I say, what's the derivative at x equals 1? It'd be, what's the slope of the tangent line there? Well, it's the slope of the line. It's 3. Another way to think of that, with a little bit more mechanics, is that we would do the derivative of 3x with respect to x plus the derivative of 2 with respect to x. Sums and differences can be broken apart. Remember, products and quotients cannot. That's why we have a product rule and a quotient rule. Well, when we use our constant multiple to bring the constant out front, we get 3 times dx dx, which is 1. And the derivative of any constant is 0. So we still arrive at that 3, but it's really just the slope of the line for graphical reasons. And then the next one, for sums, we can do the derivatives separately. The derivative of x with respect to x is 1, or the slope of the line, y equals x, which is 1, plus the derivative of tangent is secant squared. So these can all be done. They're not functions inside of functions. So those can be done with methods in the first part of the chapter, right? But now over here in this green column, we have functions inside of functions, not being multiplied, not being added or subtracted or divided, but functions within functions, or composition of functions. In this scenario, the g of x would be x squared plus 1. F of x would be the square root of x. Okay? This one is f of g of x. G of x would be 6x. F would be sine. Okay? And we're going to call this g of x the gum. Sometimes I've called it the guts, but I think I'm going to go with the gum this year. So f of g of x right here. And this is also the first part we can do. The derivative of x is 1, but what's the derivative of tangent of x squared? That's a function, it's a parabola inside of a trig function. So that's also of the form f of g of x. For those, we need something called the chain rule. Okay? So the chain rule is used when we have functions inside of functions and we're taking their derivatives. This definition of it is kind of hard for kids to get their brain wrapped around at first. Just understand that it doesn't really matter when that part of it, oops, my iPad fell down. When that part of it clicks, as long as it eventually does by the time we get to some word problems. More importantly today, you'll be able to execute this one and understand this one much easier. So this guy right here, the one that's harder to understand, we'll talk about it first, but then when we go do the examples, I'm going to gravitate towards this second expression, okay? So we're going to think of this as like a blow pop, right? The outside shell, or the outside function's the candy. The inside function is this green gum in here, right? And we're going to be calling that the U, or the G of X. So it's the G of X or the U in this scenario. And it's the gum. Okay? So let's just go practice identifying what's the gum and what's the shell. Okay? So the first thing we need to do is see these as a function within a function. You might say, hey, I could do quotient rule on letter A, and you could. But you couldn't on B, C, or D. So sometimes two methods will work. So maybe I'll go back and do this one when we're done breaking these apart, both with the chain rule and with the quotient rule, so you can see it getting the exact same answer, just in two different forms. So to use the chain rule, we need to see the inside function, which I'm going to call the gum, or the U, and the outside function. In this case, it'd be to the negative first, because that's what it means when you have something in the denominator like that, is it's x plus 1 to the negative first. So in this case, if I say, what's the inside function? If I say, what's U? Or if I say, what's the gum? You'd say, U is equal to x plus 1. It's the inside part of the function within the function. So when we say y is equal to f of u, in this scenario, f is the candy shell. So I would say y is equal to my u to the negative first. Okay, that just to follow the breakdown of it. Okay, now the next one. This is really the sine of 2x. It's a linear function inside a trig function. The g of x, or the u, or the gum in the breakdown is 2x. It's the inside function. So if we were to write this, and again, I'm not taking derivatives yet, we're just breaking them down, okay? I would say y is equal to sine of u. Next, this is a function, it's a quadratic, inside of the square root function. So if I wrote it as a function inside of a function, it would look like that. Again, u is the gum. The other function is the candy shell. Okay, so I'm going to be saying, what's the gum? Okay, sometimes I say, what's the guts? But it's the g of x in this scenario over here. All right, so my u is 3x squared minus x plus 1. So y would equal my u to the 1/2 power. The next one, when you see these little embedded powers, from here on out, I would like you to pull them outside of the entire trig function and write it like that. Be careful you don't write it like this, because that's different. That's taking the tangent of x squared. What we want to do is take the tangent of x and square it. So I prefer that when you see that embedded like that, you rewrite it so you can see that inner gum and you can identify, and you can identify the outer shell. So let's talk about what this means up here when it says, and again, I'm talking about the more difficult one first because technically I really want to focus on this. I just do think, and having taught this for so long, this representation can take a while to click. So For execution purposes, we're going to use the other. By the end of the year, you need to be comfortable with both. Okay, so what does this mean when it says dy dx is dy du times du dx? I think what I'm going to do is explain it with this trig one right here. All right, so let's talk about dy dx being dy du. Okay, so if I go right here and have y as a function of u, and I say, well, what is the derivative of sine u? It's like sine x dx. That's what this means. And then it says times du dx. Well, remember my u is 2x, so I'm really doing the derivative of 2x dx. So when I'm done with this, all right, take a look at what I would get. The derivative of sine u is cosine u. The derivative of 2x is 2. But this problem wasn't about u, right? It was a function of x. So what we do is we back substitute our u choice and we say it's cosine 2x times 2. That's kind of complicated way to think about it. So I'm going to now talk about it in terms of the blow pop and in terms of the f and the g of x, because I do think that's how you're going to want to think about it. But like I said, I think there have been years in the past where I haven't even talked about this dy, du, du, dx method, but it affects you in Calc 2. And I don't want to get into the details of why. So I am talking about it right now so that it's familiar when we have to use it, but you won't have to use it for a while. More importantly, we're going to talk about, and I'm going to go back to that letter B right here. We're going to talk about it in terms of F and G. And this is G, it's the gum or it's the guts, and sine is the candy shell. What this method says to do right up here, I'm going to go in yellow, is that you take the derivative of F and you don't touch the gum. It's kind of like when you eat the blow pot. You need to take care of the candy. You don't just crack in to get the gum or you're going to break your teeth. And you're going to break this derivative if you don't deal with the outer function first. So when it says f prime g of x, you say, well, what is the derivative of sine? It's cosine. And don't touch the gum. Okay? That took care of the outer shell. And then we say, well, what is the derivative of the gum? Or the derivative of the guts? What is the derivative of 2x? It's 2. Do you see how we got the same answer? It's just a little bit more user-friendly. So we're going to go do that with this one up here. My dy dx, my gum, is x squared plus 1, or my g of x. My f of x is the cubing function. So we're going to sort of pretend that's u cubed, and we do 3u squared. But this is what we do. We deal with the power first. We bring it out front. We don't touch the gum. We drop the power down 1. That took care of the outer shell, or the outer function. It was a quadratic function embedded in a cubic function. So you take care of that outer shell first, then times, now you deal with the gum. The derivative of the guts, which is 2x. What we just did is f prime of g of x times g prime of x. This being g prime, this being f prime of g of x. When I clean it up, I get a 6x times x squared plus 1 quantity squared. And that rule is called the general power rule, that whenever you see a function to a power, you can just bring that power out front, knock it down 1, and multiply by the derivative of what I call the guts or the gum. So now let's see if you kind of watch how quickly these can go if you view it as gum and candy. Here's my gum, don't touch it. I bring the power out front, I leave the gum untouched, I drop the power down 1. That's this part of it, n times u to the n minus 1. And in this case, this is the u. I like to call it the gum or the g of x, but just so you get how it works. If I had u cubed, and I said, hey, what's its derivative? You would say 3u squared, okay? But u is 3x minus 2x squared. So we put that back in. Times the derivative of the gum, okay? The derivative of 3x minus 2x squared is 3 minus 4x. So when I clean this up, maybe you want to call it 9 minus 12. I like things factored because usually, to be honest, what we use derivatives for is finding when rates of change are 0, because that's when things stop going from increasing to decreasing or vice versa, and they're going to eventually allow us to optimize functions or find their highest or lowest points. So usually what we'll be doing with our derivative, remember it's the slope of a tangent line, is we'll be setting it equal to 0. And it's easiest to see zeros if your derivative is completely factored. Now if I said what are the zeros, you'd say, oh, and I could probably take an x out of that as well. I'm not going to rewrite it right now. But let's not talk about zeros because today it's all about the chain rule, which is used for functions inside a function. Remember when you have the radical, we want to see that power and the roots on the bottom. So there's my function inside of a function. My outside function is a power function. I bring it out front. So I'd say y prime or dy dx is 2/3. Do not touch the gum. I drop the power 1 disguised as denominator over denominator. So I'd have negative 1/3. Now I have times the derivative of the guts. Or now I can chew on the gum. So times 2x. We don't leave negative exponents, so we're going to write this as 4x, taking care of this guy and this guy, over 3. And we're going to send the x squared minus 1 to the denominator. And I think I'll go back to root form because I always like it when we answer it in the same form as the original problem. But I won't mark it wrong if you put to the 1/3 down there. All right. Last one of this type here on this page. So my dy, and this is just, it's called the chain rule because you can have f of g of h of k of x. You can have functions inside of functions, 19 of them, and you still work on the outer shell first. Usually at most that we'll have is 4 of them. We're going to practice a triple on the next page here, but this would be written as 7 times. You might say, I want to use the quotient rule on this one. You certainly could, okay? So, but you couldn't on the other two. So, and I'll show you the quotient rule on it because I promised I would on one where it could go either way. But if I want to see this as a function inside of a function, there I go. So I really am seeing this as u to the negative 2. Okay, and what do? I bring the power out front. And, oops, I have a linkage error right here. Those are deadly. That's not what dy dx is, that's what y is. dy dx is equal to 14. I'm bringing the negative 2 out front. I am not touching u. I'm not chewing on that gum yet. I drop the power, and then I multiply by the derivative of the guts. The guts being 2x minus 3, its derivative being 2. So I end up with a 28 over, because we don't leave negative exponents. Put that in your head. We don't leave negative exponents. So there's my derivative. Keep in mind what it does. It still gives us the slope of the tangent line at any part on the graph of this function. So if I said, when x is 4, what's the slope of the tangent line? You would put it in here. If I said when x is 4, what's an equation for the tangent line? You'd put 4 in y to get 4 comma the point, and 4 in the derivative to get the slope. So there's still those questions hanging out there, but we're practicing chain rule today. Now, I'm going to go back and erase all this right here, and I'm going to launch into it with the quotient rule. So suppose little Billy sees a quotient. He's like, LaRue taught us the quotient rule. I want to use it. Here it goes. Low d high. The derivative of a constant is 0 minus, so it's going to become a plus, high d low. Derivative, right? Draw a line and square below. Now, it doesn't look much like this guy, but watch. When I do d low, it's the chain rule. So if I'm going to launch into the quotient rule on this one, the chain rule's popping out right now because the derivative of the low function, the 7's just hanging on, is bring the power out front, drop it down 1, now do the derivative of the guts, and it's all over the 2x minus 3 to the 4th. Well, one of these will cancel with one of those, giving us our denominator. And the top becomes the 28. So you'll notice my end game, even with the quotient rule, was the same. So you might say, well, which one do I use? I always say that when I'm doing the quotient rule and the derivative of the top or the bottom is 0, meaning there's a constant as either the entire numerator or the entire denominator, don't use the quotient rule. So notice how I said when I did D high, I got a 0. That made me go, nah, I'm going to do a different rule. All right, so the trig functions are really common times where we see the chain rule, and it works the same way. You just have to remember the derivative of sine, cos. You have to know all your derivatives. So again, my outside function is sine. I am going to take care of that candy first. So this will be cosine of 2x times the derivative of the guts, which is 2. And I'm done. Okay? It's a function inside of a function. The derivative of sine x is just cosine x. But to be honest, if I use the chain rule on it, if you're like, there's still a function inside a function, the root, I'd say, sure. Yep. It'd be cosine x times the derivative of x with respect to x. Well, that's 1. So, there. Right? So in this one, the derivative of the outside function, or what we call the f prime, because remember, we're thinking of this as f of g of x, okay? The f prime is the derivative of cosine, which is, notice all the cofunctions derivatives are negative, so that should help you. So it's going to be negative sine of g of x, so it's equaling the outside's derivative while keeping the gum intact, times the derivative of the gum, or times du dx. Sorry, so that's going to be a 3. So I'd have a negative 3 sine 3x minus 1. This is just 2 links in the chain here. There's just 2 functions. So on this next one, I challenge you to pause and try it on your own, but I need the derivative of secant, which is secant tangent, but this will be secant u tangent u. So my derivative will be secant gum, u gum, tangent gum times derivative of gum. And then we bring the 4 out front. You always put your less complicated functions at the beginning of the train. All right, so last step. Now we're going to go from the blow pop, the 2 layers, to the peanut M&M with 3 layers. Okay? We might get up to 4. There might be a couple where there's 4, but honestly, adding another link to the chain doesn't really make it more difficult. It just makes your answer longer. So when we have function inside a function, we have to deal with the candy coating first. So here's my green M&M. Once I deal with that, I attack the chocolate. Once I deal with that, I attack the peanut center. So we do derivative of the candy, derivative of the chocolate, and derivative of the peanut. So now, first thing you need to do is sort of identify all those layers or all those links in the chain. So my outer function is actually a quartic. Okay? That's the candy coating. I deal with it first, and I don't touch the chocolate, and I don't touch the peanut. It's like you're sucking off the candy shell. So when I do my derivative, I bring that power out front. I do not eat the chocolate. That's the biggest mistake with these is kids will do a 2 in one step. And I'll say you just killed off 2 links in the chain, or sometimes I'll say you just broke your teeth, you bit through the candy, or I'll say you ate the chocolate. It's all the same stuff, but a lot of times kids will see that sign and they're dying to change it to a cosine. You can't do that until you've dealt with the power. So sometimes when kids struggle with those links, I'll say cross it off. Okay, now deal with the sine, or the chocolate. The derivative of sine is cosine. Do not touch the peanut. The derivative of 3x is 3. There were 3 functions, 3 links in the chain, and when I clean it all up, I'd have 12 times sine of 3x times cosine of 3x. Second to the last one. Sorry, the notes are long, but it is what it is. This is a huge topic, and actually they're long for me. I think you're used to having really long notes, so you still shouldn't be mad at me. All right, I have a line, 1/2 x, stuffed inside a trig function, stuffed inside the square root. So again, we're going to work at it from the outside in. Don't even look at the chocolate or the peanut. Deal with the 1/2. You bring it out front. You do not touch the inner links. You drop the power 1. Then you deal with the chocolate. The derivative of secant is secant tangent. That needs to be memorized. So we do secant, but we keep the peanut there. Tangent, we keep the peanut there. Times the derivative of x over 2. The derivative of 1/2 x is just the slope of the line, or just 1/2, or you can think of it as a half times dx dx. You can still think of it as the chain rule, but dx dx is 1. So that's just times 1/2. We would clean that up in a couple ways. We would lead with 1/4, and we would put this guy in the denominator as the square root, but I'm running into my candy, so I'm just going to let you clean that one up on your own. And to wrap it up here, and don't turn this off yet, because I'm going to tell you I have 7 questions in here. There's 3 more points coming from something else. Okay, so, and that's your assignment for Tuesday, Wednesday, and I will record it on Thursday. Like, I'll put it in my grade book on Thursday. So technically you have until my prep hour in the morning on Thursday. So let's do cotangent 3x over 2, right? So again, we have a line inside of a trig function, right? All to the 2/3 power. And again, I challenge you to pause the video. If we were doing this in class, I'd say, you guys go try this. Have you check it with a partner. But like I said, we lose all that with our hybrid model here. So 2/3, don't touch the cotangent, don't touch the peanut, knock the power down 1, disguised as 3/3. I'm going to have to move up into, I'm going to have to move past my M&Ms here. So that just took care of the 2/3 power. What is the derivative of tangent? Cotangent, I mean. The derivative of tangent is secant squared. Cotangent is negative cosecant squared. We don't touch the guts or the peanut. The derivative of 3/2 x is just 3/2. And again, it looks uglier than it actually is, but we would need to go clean this up. We have a 2/3 constant. We have a 3/2 constant. Those are going to cancel each other out. We have a negative that should come out front. Where can I write that answer? Let's get some real estate in the middle here, huh? So let's go take care of the negative. This killed this. The cosecant squared can stay on the top. The negative 1/3 for the cotangent is going to throw it down on the bottom. You can write to the 1/3, but I like it in the original form. All right, that's it. So your other 3 points are to go to Delta Math, and there'll be a chain rule 3 problem little test where I think I'll just keep it at 2 links in the chain. Okay, so Delta Math for 3 problems. We'll wrap this up and we'll be at 10 out of 10, and when I do them this way, I test point them. Okay, have a good one.